On an ordinary summer evening, life across the Bay of Naples seemed destined to follow its familiar rhythm. Families gathered along waterfront promenades. Restaurants welcomed diners beneath fading sunlight. Tourists wandered through ancient streets built atop one of the most closely watched volcanic systems on Earth. Then, in an instant, calm gave way to alarm as an immense jolt surged through the ground with a force not experienced in decades. Apartment buildings rattled violently, walls cracked, furniture lurched across rooms. People rushed into the streets, fearing that something far greater than an earthquake might be unfolding beneath their feet. Italy had just witnessed the strongest earthquake to strike the Campi Flegrei volcanic caldera in approximately 40 years. Was this simply another chapter in the restless life of one of Europe's most active volcanic regions, or did the powerful shaking signal a deeper change unfolding beneath the densely populated landscape west of Naples? Why did scientists immediately begin examining not only the magnitude of the earthquake itself, but also every tremor that followed? Most importantly, why did officials urge calm even as hundreds of earthquakes continued rattling the region over the following days? At exactly 7:46 in the evening local time, on Friday, July 31st, a magnitude 4.7 earthquake struck the Campi Flegrei volcanic area, according to Italy's National Institute of Geophysics and Volcanology, known by its English abbreviation National Institute of Geophysics and Volcanology, or INGV. The epicenter was located near the Solfatara crater in Pozzuoli, while the earthquake originated at a shallow depth of roughly 2 miles, or about 3 kilometers. That relatively shallow depth made all the difference. Earthquakes occurring close to the surface lose far less energy before their seismic waves reach buildings and people above. Even moderate earthquakes can therefore feel extraordinarily violent when they originate only a few miles, or several kilometers, underground. Across Pozzuoli and western Naples, residents described prolonged shaking that seemed unusually intense compared with previous earthquakes they had experienced during recent years of volcanic unrest. Within moments, emergency calls flooded local authorities. People fled apartment blocks without waiting to collect their belongings. Some discovered that doors had warped or jammed after buildings shifted during the shaking. Pieces of masonry crashed into narrow streets. Decorative cornices broke loose from aging buildings that have stood for generations. Power interruptions spread through parts of the area, while emergency responders rushed to assess structural damage before aftershocks could worsen already weakened buildings. The earthquake represented far more than another entry in Italy's long seismic history. For scientists monitoring Campi Flegrei, the magnitude 4.7 event immediately became the largest earthquake recorded during the current phase of volcanic unrest, and the strongest to affect the caldera in roughly 4 decades. Previous earthquakes during the ongoing bradyseismic crisis had steadily increased in strength over recent years, including several events exceeding magnitude 4. Yet none had reached this level until now. Damage was concentrated around Pozzuoli, the community closest to the epicenter and situated directly within the ancient volcanic caldera. Inspection teams documented cracked building facades, damaged roofs, collapsed sections of masonry and instability affecting numerous residential structures. Authorities evacuated hundreds of residents from homes deemed unsafe until engineers could determine whether they remained structurally sound. Temporary shelters were opened for families suddenly unable to return home, while emergency personnel worked through the night, responding to hundreds of requests for assistance. Several injured residents required hospital treatment after falling debris struck buildings or damaged infrastructure. Although authorities confirmed there were no immediate fatalities, the earthquake served as a powerful reminder that even relatively moderate volcanic earthquakes can produce significant consequences when they occur beneath densely populated urban areas. Transportation networks also felt the impact. Rail services were temporarily suspended while engineers inspected tracks, tunnels and bridges for possible damage. Sections of public transportation remained closed until safety inspections confirmed they could resume operations. Emergency managers understood that after a strong earthquake, hidden structural weaknesses can pose risks long after the initial shaking has stopped. Yet even as emergency crews responded above ground, another operation was unfolding inside scientific monitoring centres across Italy. Almost immediately after the main earthquake, seismologists began analysing thousands of incoming data points from an extensive monitoring network surrounding Campi Flegrei. Every seismic station, ground deformation sensor, satellite measurement and volcanic gas instrument suddenly became part of a much larger effort to answer one essential question. Was the volcanic system changing? The answer would not come from the magnitude 4.7 earthquake alone. Instead, scientists focused intensely on everything that happened afterward. During the first night following the earthquake, dozens of additional tremors rippled through the caldera. By the following day, the number had climbed dramatically. According to the latest INGV bulletins, the earthquake sequence eventually reached approximately 191 recorded earthquakes. Despite the growing number of tremors, one detail immediately caught the attention of researchers. None of the aftershocks exceeded the magnitude 4.7 earthquake that initiated the sequence. That observation may seem minor to the general public, yet to volcanologists and earthquake specialists it represents one of the most important characteristics of the ongoing swarm. Earth's crust rarely releases accumulated stress through a single clean break. Instead, large fractures redistribute stress into neighbouring sections of rock, producing numerous smaller earthquakes as surrounding faults gradually adjust to their new conditions. Campi Flegrei appears to be following precisely that pattern. Rather than generating progressively larger earthquakes, the caldera has continued producing many smaller ones. Each event releases another portion of stored mechanical energy without surpassing the original earthquake in magnitude. Scientists remain cautious. They know earthquake sequences can evolve unpredictably. Additional strong earthquakes cannot be ruled out simply because none has occurred yet. Nevertheless, the current behaviour offers an encouraging indication that accumulated strain may be dissipating through numerous relatively small adjustments instead of concentrating toward an even larger rupture. That subtle distinction explains why every official bulletin from INGV has carefully tracked not only the number of earthquakes, but also their individual magnitudes. The observatory specialists are watching whether seismic energy continues being released gradually or begins concentrating into increasingly larger events. At present, the latter has not happened. Understanding why requires looking far deeper than the earthquake itself. Campi Flegrei is unlike almost any other volcanic system in Europe. Although many people immediately think of nearby Mount Vesuvius whenever Naples appears in headlines, the sprawling Campi Flegrei caldera presents an entirely different geological challenge. Rather than forming a steep volcanic cone rising dramatically above the surrounding landscape, Campi Flegrei is an enormous collapsed volcanic basin covering roughly 8 miles by 9 miles, or approximately 12 by 15 kilometres. Much of the caldera lies beneath the Bay of Pozzuoli, while its remaining portions support thriving cities, ancient Roman ruins, industrial districts and residential neighbourhoods housing hundreds of thousands of people. Many residents drive across its surface every day without realising they are travelling inside the remnants of one of Earth's largest volcanic collapse structures. The landscape itself tells the tale. Circular craters filled with lakes, steaming fumaroles releasing volcanic gases, hot springs, uplifted coastlines and broad volcanic hills all reveal the immense geological forces that shape this region over tens of thousands of years. Among the best-known features is the Solfatara crater, located close to Friday's earthquake epicenter. Rather than erupting lava today, Solfatara continuously emits steam, carbon dioxide, hydrogen sulfide and other volcanic gases through numerous fumaroles. The unmistakable smell of sulfur drifting across parts of the crater serves as a daily reminder that enormous quantities of heat remain trapped beneath the surface. For volcanologists, Solfatara functions almost like a natural observation window into the hydrothermal system hidden below Campi Flegrei. The gases escaping there provide valuable clues about changing underground conditions, allowing scientists to monitor pressure, temperature and chemical composition over time. Those measurements become especially important whenever earthquake activity suddenly increases. Because earthquakes represent only one part of a much larger volcanic system, researchers continuously compare seismic data with ground deformation measurements, gas chemistry, satellite observations, and precise global positioning system stations distributed across the caldera. Only by combining all those independent observations can scientists determine whether Campi Flegrei is simply experiencing another episode of bradyseism, or whether something fundamentally different may be developing. For decades, Campi Flegrei has challenged one of the most common assumptions people make about volcanoes. Many imagine that eruptions begin only when glowing magma starts racing toward the surface. The reality is far more complex. Long before molten rock ever threatens to erupt, an entire volcanic system can begin changing deep underground. Rocks fracture, underground fluids migrate through ancient cracks, gases accumulate beneath impermeable layers, and the surface itself slowly rises and falls over periods ranging from months to decades. Campi Flegrei has been demonstrating precisely this behaviour, making every significant earthquake far more than an isolated seismic event. Scientists refer to this slow vertical movement as bradyseism, a phenomenon that has defined the Phlegreian fields for thousands of years. The name comes from Greek words meaning slow movement, yet the consequences can be anything but subtle. During periods of uplift, entire coastlines gradually rise above sea level. Ancient Roman ruins around Pozzuoli preserve remarkable evidence of these changes. Marble columns at the Temple of Serapis contain bands of holes drilled by marine shellfish, revealing that the structure spent centuries submerged beneath seawater before slowly rising above the bay once again. Few places on Earth preserve such a clear geological record, showing that an entire city has repeatedly moved up and down through history. The current phase of bradyseism began in approximately 2005. At first, the changes were almost imperceptible. High-precision global positioning system receivers detected only a few millimeters of uplift each year. Then the pace gradually accelerated. By the early 2020s, the centre of the caldera around Pozzuoli was rising at rates measured in several centimetres annually. Today, cumulative uplift since the present unrest began exceeds 4 feet, or more than 1.3 metres in some areas. That may not sound dramatic compared with the height of a building, but from a geological perspective it represents an extraordinary amount of deformation affecting an entire volcanic caldera. Imagine lifting an enormous bowl-shaped section of Earth's crust several miles or several kilometers across by more than the height of an average adult. Such movement cannot occur without placing tremendous stress on the surrounding rocks. Eventually, those rocks begin to fail. Each fracture generates an earthquake. This is precisely why seismic swarms accompany bradyseism. As the caldera inflates, ancient faults repeatedly crack to accommodate the expanding ground. Every earthquake represents another adjustment, as the crust attempts to relieve the pressure building beneath it. The latest sequence appears to illustrate exactly that process. According to the most recent bulletins issued by INGV, approximately 191 earthquakes have now been recorded since the magnitude 4.7 event struck near Solfatara. Remarkably, none has exceeded the initial earthquake in size. Instead, dozens upon dozens of smaller tremors continue redistributing stress through the fractured volcanic crust. That pattern is one reason scientists have not declared a major change in the volcano's behavior. Fabio Florindo, president of Italy's National Institute of Geophysics and Volcanology, emphasized after the earthquake that one large tremor alone cannot determine whether Campi Flegrei is moving toward an eruption. Researchers instead evaluate every available monitoring system simultaneously, including seismic activity, ground deformation, volcanic gas emissions, geothermal temperatures, satellite observations, and changes in underground pressure. So far, those combined observations do not indicate that magma is rapidly ascending toward the surface. Instead, much of the evidence continues pointing toward intense deformation within the volcano's hydrothermal system. Deep beneath Campi Flegrei lies an enormous network of groundwater, steam, dissolved volcanic gases, and extremely hot rocks heated by underlying magma. This hydrothermal system behaves somewhat like a giant underground pressure cooker. Water circulating through fractures becomes superheated, generating steam that occupies far more volume than liquid water. Carbon dioxide released from deeper magma accumulates within porous rocks, further increasing underground pressure. Eventually, that pressure becomes too great. Rock fractures. Another earthquake occurs. Several recent scientific studies suggest this mechanism explains much of the caldera's present seismicity. Rather than fresh magma forcing its way upward, increasing pressure within the hydrothermal system may be repeatedly breaking weakened rocks already stressed by years of uplift. That distinction is critically important. If earthquakes primarily result from hydrothermal pressure, they can continue for extended periods without necessarily leading to an eruption. Campi Flegrei experienced similar behavior during previous decades, including the major bradyseismic crisis between the early 1980s and the middle 1980s. That historical episode remains one of the most valuable comparisons for understanding today's unrest. Beginning in the early 1980s, Pozzuoli experienced an extraordinary increase in seismic activity. Thousands of earthquakes struck the region over several years, while the ground rose by approximately 6 feet, or nearly 2 meters. Entire neighborhoods became increasingly unstable as repeated shaking damaged buildings designed long before modern seismic standards existed. Authorities eventually evacuated more than 40,000 residents from Pozzuoli's historic centre. The city became nearly deserted. Yet, despite years of earthquakes and dramatic uplift, no eruption followed. Pressure gradually subsided, earthquake activity decreased, and Campi Flegrei returned to a quieter state without producing lava or ash. That history explains why scientists remain cautious today. Large earthquake swarms alone do not guarantee an eruption. Neither does substantial ground uplift. Neither even requires magma to reach the surface. Every volcanic crisis evolves differently, making continuous monitoring far more valuable than focusing on any single event. Nevertheless, Friday's magnitude 4.7 earthquake crossed an important psychological threshold. Although only 1/10 of a magnitude unit, stronger than last year's magnitude 4.6 earthquake, the difference is not trivial. Earthquake magnitude follows a logarithmic scale rather than a simple numerical progression. Each increase represents a significant jump in released energy. More importantly, magnitude 4.7 now stands as the strongest earthquake recorded during the present bradyseismic crisis. It also approaches a level that volcanologists have long viewed with increasing concern. A magnitude 5 earthquake inside Campi Flegrei would not necessarily indicate an imminent eruption. However, it would represent a significant escalation in the amount of stress being released by the volcanic system. Why is that threshold so important? The answer lies beneath the streets of Pozzuoli. Unlike many tectonic earthquakes occurring along major plate boundaries, Campi Flegrei earthquakes originate within highly fractured volcanic rocks directly beneath densely populated communities. Their shallow depth means very little seismic energy is lost before reaching buildings above. A magnitude 5 earthquake occurring only about 2 miles or 3 kilometers beneath the surface would therefore produce considerably stronger shaking than a deeper earthquake of identical magnitude. Engineers estimate that shallow volcanic earthquakes generate higher peak ground accelerations capable of severely damaging older masonry structures. Campi Flegrei is filled with exactly those kinds of buildings. Pozzuoli contains centuries-old churches, stone apartment blocks, historic arches, narrow streets, and aging infrastructure constructed long before modern earthquake-resistant engineering became standard practice. Even many reinforced buildings have already experienced years of repeated shaking from hundreds of smaller earthquakes. Each event weakens mortar. Each fracture expands existing cracks. Each vibration slightly reduces structural integrity. Consequently, a future magnitude 5 or larger earthquake would not simply strike undamaged buildings. It would strike structures already stressed by years of ongoing seismic activity. Another reason a magnitude 5 event would concern scientists involves the state of the volcanic crust itself. Producing progressively larger earthquakes may indicate that stress is no longer being released through numerous small fractures, but instead is beginning to accumulate along larger fault segments. That possibility is precisely why INGV continues carefully examining every aftershock. Thus far, the encouraging observation remains unchanged. The swarm continues producing many relatively small earthquakes. None has exceeded the original magnitude 4.7. That suggests the crust is still releasing accumulated strain incrementally rather than concentrating energy into progressively larger ruptures. Even so, researchers cannot assume that trend will continue indefinitely. Earthquake sequences sometimes change unexpectedly. A stronger event remains entirely possible. For that reason, monitoring stations surrounding Campi Flegrei now operate continuously, collecting enormous quantities of information every second. Hundreds of sensors distributed across the caldera measure microscopic ground movements, detect tiny earthquakes invisible to people, analyze volcanic gas chemistry, record changes in groundwater levels, and monitor subtle variations in Earth's gravitational field. Orbiting satellites contribute another crucial layer of surveillance. Using interferometric synthetic aperture radar, commonly known as INSAR, scientists compare radar images acquired weeks apart to detect ground movement measured in mere millimeters across the entire caldera. These remarkable observations allow researchers to determine exactly where uplift is accelerating and whether deformation patterns are changing after each significant earthquake. Every new dataset becomes another piece of an extraordinarily complex geological puzzle. One question has dominated scientific discussions ever since the magnitude 4.7 earthquake struck Campi Flegrei. Was this simply another tectonic earthquake generated by movement along a fault, or did it originate from the volcanic system itself? The distinction matters enormously because the answer shapes the way scientists interpret the entire sequence now unfolding beneath western Naples. At first glance, the earthquake resembles many ordinary tectonic earthquakes. According to seismic data, the event occurred at approximately 5 kilometers, or just over 3 miles, beneath the surface, with its epicenter located immediately west-northwest of Torre Caracciolo, near the Solfatara area. Earthquakes happen every day because rocks eventually break when subjected to enough stress. Whether that stress comes from moving tectonic plates or an inflating volcano, the immediate mechanism is remarkably similar. A fault suddenly slips, releasing stored elastic energy that radiates outward as seismic waves. Yet identifying what created that stress is where Campi Flegrei becomes unique. This was not a classic tectonic earthquake like those that commonly occur along the Apennine fault system crossing central Italy or along major plate boundaries around the world. Those earthquakes are primarily driven by the slow motion of Earth's tectonic plates, which constantly pull, compress or slide past one another over millions of years. Campi Flegrei sits in an entirely different geological environment. Here, the dominant force is the volcano itself. Researchers describe the recent seismicity as volcano-tectonic earthquakes. The name reflects the fact that the immediate earthquake mechanism is tectonic fault rupture, but the stress causing that rupture originates from volcanic processes occurring beneath the caldera. In other words, faults are breaking because the volcanic system continues deforming the surrounding crust. Imagine inflating a balloon beneath a thick concrete floor. At first, the floor barely moves. As pressure increases, tiny cracks begin appearing. Continue inflating the balloon, and eventually larger fractures develop as the concrete struggles to accommodate the expanding force beneath it. Campi Flegrei behaves in much the same way. Instead of air inside a balloon, however, pressure comes from an intricate combination of hot fluids, volcanic gases, groundwater and heat supplied by magma stored several kilometers or several miles below the surface. This explains why scientists avoid describing Friday's earthquake as purely magmatic. A true magmatic earthquake generally occurs when molten rock actively forces its way through surrounding crust, fracturing rocks as magma opens new pathways toward the surface. Such earthquakes are often accompanied by several additional warning signs. Scientists look for rapid changes in earthquake depth, migration of seismic activity upward through the crust, accelerated ground deformation, major shifts in volcanic gas chemistry, increasing sulfur dioxide emissions, and other indicators suggesting magma is physically moving toward eruption. At Campi Flegrei, those signals have not appeared. Following the magnitude 4.7 earthquake, INGV carefully examined data from every component of its monitoring network. Seismic stations continued recording aftershocks. Continuous global positioning system receivers measured ground movement. Tilt meters searched for sudden deformation. Satellite observations compared changes in surface elevation. Instruments around Solfatara analyze carbon dioxide, sulfur dioxide and other volcanic gases escaping from fumaroles. Taken together, those observations did not indicate a fundamental change in the volcanic system. That conclusion is exactly why INGV President Fabio Florindo urged the public not to interpret one large earthquake as evidence that an eruption had become imminent. Every monitoring parameter must be considered together before scientists can conclude that magma is ascending toward the surface. Instead, the current evidence points toward a continuation of the ongoing bradyseismic crisis. The caldera has been slowly inflating for nearly 2 decades. As pressure gradually increases within the hydrothermal system, faults repeatedly fracture, producing earthquake swarms remarkably similar to the one now continuing beneath Pozzuoli. The location of the earthquake also supports this interpretation. Its epicenter lies near Solfatara, one of the most active hydrothermal regions inside Campi Flegrei. Steam continuously escapes through fumaroles there, accompanied by abundant carbon dioxide and other volcanic gases. Those gases originate ultimately from magma residing deep below the caldera, but they accumulate within a vast hydrothermal system long before reaching the surface. As pressure builds inside that hydrothermal reservoir, surrounding rocks become progressively weaker. Laboratory studies have demonstrated that hot water circulating through fractured volcanic rocks gradually alters their mineral composition, making them significantly more susceptible to failure. Carbon dioxide further increases underground pressure while reducing the strength of already fractured rocks. Eventually, relatively modest increases in pressure can trigger surprisingly energetic earthquakes. Recent scientific research has strengthened this interpretation even further. Several studies published over the past few years conclude that the current unrest is strongly influenced by hydrothermal pressurization rather than by rapid upward movement of fresh magma. That does not mean magma is absent. Campi Flegrei remains an active volcanic system, and its deep magma reservoir continues supplying heat and volcanic gases. However, the earthquakes themselves appear to be generated primarily because hot fluids and gases are increasing pressure within the shallow crust, causing existing faults to rupture. This distinction explains another observation that has reassured many volcanologists. Since the magnitude 4.7 earthquake occurred on Friday evening, the sequence has expanded to approximately 191 earthquakes. If fresh magma were rapidly intruding upward, scientists might expect seismic activity to migrate vertically as magma forced open new fractures through the crust. Instead, the earthquakes have remained concentrated within the same general area, while gradually decreasing in magnitude. None has exceeded the original magnitude 4.7 event. To seismologists, that pattern resembles a classical stress-release sequence rather than an accelerating magmatic intrusion. Nevertheless, researchers remain extremely cautious. Campi Flegrei has earned worldwide attention precisely because volcanic systems can evolve in unexpected ways. Conditions capable of producing hydrothermal earthquakes today could change over weeks or months if deeper magma begins injecting additional heat or gases into the system. That possibility is why scientists refuse either to dismiss the unrest or to exaggerate its significance. Every earthquake, Every millimetre of uplift, every change in volcanic gas chemistry and every subtle variation in underground pressure becomes another clue helping researchers understand what the volcano is doing beneath one of Europe's most densely populated metropolitan regions. The stakes could hardly be higher. Approximately 500,000 people live within the Campi Flegrei caldera itself, while more than 3 million people occupy the greater Naples metropolitan area surrounding both Campi Flegrei and Mount Vesuvius. No other active volcanic system of comparable size exists beneath such a densely populated urban environment. For now, however, the scientific consensus remains remarkably consistent. The magnitude 4.7 earthquake was volcano-tectonic rather than purely tectonic or directly magmatic. The fault rupture itself behaved like an ordinary earthquake, but the forces responsible for loading that fault originated from the ongoing volcanic unrest driving Campi Flegrei's bradyseismic uplift. Current monitoring data do not indicate that fresh magma is rapidly rising toward the surface, nor do they show evidence that an eruption is imminent. Even so, the strongest earthquake in 40 years has demonstrated that the caldera continues evolving. Whether the next chapter brings gradual relief through continued smaller earthquakes or a new phase of unrest will depend on what scientists observe in the days, weeks and months ahead. Every new bulletin issued by INGV will therefore be examined with extraordinary attention, because at Campi Flegrei the most important warning signs rarely come from a single earthquake alone. They emerge from the combined behaviour of an entire volcanic system that has been breathing, rising and reshaping the landscape for thousands of years, and that remains one of the most intensely monitored volcanoes anywhere on Earth.